Okay, so today we're going to go over 6.7, and we're going to investigate corresponding ratios of right triangles with the same acute angles and what determines if two right triangles are similar. Okay, so you've already done, and sorry, last but not least, why are the ratios of sides in right triangles so special that they deserve classification of their own, which is called trig ratio. So today is a really big day in terms of um, understanding in terms of the world of math. Okay, we're going to do what we call trig, and trig sounds really, really intimidating to people, but it's not that bad. Okay, so it says draw a right triangle with an acute angle that measures 60 degrees. I actually did measure this, and so this right here is 60 degrees, and this is my right angle here, and I did it specifically because I wanted it to be a pretty accurate representation of this. And so, um, and then they say measure it, and you can do this on your own. But for today, I'm going to say that each of this side here, it says measure each side of your triangle accurately with a centimeter ruler. And my centimeter ruler says that my hypotenuse is about 1, 2, 3, 4, 5, 6.6. It's about 6.6. Okay. And how am I going to rotate this? And I can't measure the other two sides. So let me see. So I'm going to measure my other side, and it's about 3.3. These are centimeters. And my last side, and you can't see me measuring this because I am about 5.7. It's not exactly, these are a little bit off, but that's good enough for now. So it says measure each side of the triangle as accurately as you can with the centimeter rule using the 60-degree angle as a reference angle. List the measures of each of the fine. The length of the adjacent side. Okay, so you've never talked about adjacent side, so I'm going to take some time to make sure that we understand what adjacent is. Okay, let's talk about the hypotenuse. The hypotenuse in this case is 6.6 centimeters. And then, so if this is the angle we're referencing, adjacent is the side, one of the sides of the angle. So in this case, it's going to be 3.3 centimeters. Okay. And then the opposite side, now whenever I draw opposite, I always go from the angle, and it's like I'm facing that angle. Does that make sense? So this is the opposite angle. This angle is opposite this side, and this side is opposite this angle. So this is 5.7 centimeters. Now, opposite, okay, let's talk about these words super quick. Adjacent means like next to, okay? So like if you're thinking about your bedroom, right? Your bedroom shares a wall with something. Now, my daughter's bedroom, which is where I'm teaching right now, my daughter's bedroom shares a wall with the bathroom, meaning right next door to the bathroom is my daughter's bedroom. Okay. Opposite means across from. So now I want you to think about like across the street from. Okay. So like I want you to think about, I don't know, maybe your house or maybe a grocery store that you normally go to. What's across the street from it? So, excuse me. So opposite from it is across from. So that's what I need you to consistently think. Now it says create the following ratios using your measurements. Opposite side over hypotenuse. So pick up your opposite side, pick up your hypotenuse, and you're going to write it here. So it goes 5.5 over 6.7. Adjacent side over hypotenuse. So what would that be? 3.3 over 6.6. I don't know why I put 6. Wow, I put 5.5 and there's no 5.5. Sorry. And there's no 6.7 either. Let's try this again. Okay, I should have written 5.5 7 and 6.6. And last but not least, opposite over adjacent is 5.7 over 6, just kidding, 3.3. So you're going to be doing this a lot. Okay, you're going to do this a lot. It says compare your ratios with others at hand, but these are our ratios. If I was to change the sides, you would notice that the ratios would be exactly, the numbers might change, but the ratio, meaning 5.7 divided by 6.6, that whatever that equals to would be the same. Okay. In the right triangles provided, find the missing side lengths and then create the desired ratios based on the angle reference. So this is a pretty big deal. So it says, again, I'm going to read the directions again. In the right triangle, find the missing side length and then create the desired ratio based on the angle reference. Okay, so one more time. Whenever we're doing these things, whenever you see a right triangle, there's two tools that you are going to use over and over again. Whenever you see right triangles, your two tools for right triangles are the Pythagorean theorem or your trig ratio. Now, today is the first day, trig ratios. Today is the first day that you're actually learning trig ratios. So if you're like, I didn't know that, now you do. Okay. So list the ratios of triangle ABC using angle A as a reference. So the very first thing they wanted us to do was to find this. So whenever we're missing something, we're going to go to these two. So the Pythagorean theorem, just as a reminder, is leg squared plus leg squared equals hypotenuse squared. So you're going to do that. And then you're going to come back to me just as a practice. All right, now that you're back, it's 3 squared plus x squared equals 6 squared. And then so now I get 9 plus x squared equals to 36. So x squared equals to, what is that, 27. So x equals to 3 root 3 plus or minus, but I'm going to throw out the minus because we're dealing with triangles. So this is 3 root 3. Okay, if you didn't know how to do both of those, now you do. Now go in and do the triangle DEF and find EF. All right, so here's me doing it again. It's 6 squared plus y squared equals 12 squared. So that's 36 plus y squared equals to 144. So then that means y squared equals to 108. And when I square root that, let's see, I get 54 and 2. I get 9 times 6, 3 times 2, and 3 times 3. So then I get 3 times 2, which is 6 root 3. So y is equal to plus or minus 6 root 3. And I take out that negative again. So your brain should be like, hey, that's kind of neat how they both had root 3s. Your brain should also be like, hey, there's some numbers here that kind of like I can get to. And if your brain noticed that, awesome. And it's because it's still in the similarity chapter. And if you notice, these sides are half of these sides. So 3 is half of 6. 6 is half of 12. 3 root 3 is half of 6 root 3. Okay. Another way to say it is these are double those sides. All right. So this is what I want you to practice. I want you to find the opposite over the hypotenuse for these triangles. I want you to do all of these. And then I want you to see if there's anything that you notice. And then come back to me when you're done so that we can go over our answers and see what you noticed. Okay, so now that you're back, it says to use angle A as your reference angle. So I'm going from this angle and I'm going to go for the opposite side over the hypotenuse. Now the hypotenuse is always your hypotenuse. It's always going to be 6 on the bottom. So I'm going to put a 6 on the bottom there. Okay. Okay, now it's asking for the opposite side. The opposite side of angle A. So sometimes I pretend that this is like, this is a weird story, but this is like, does everybody see like how this could be an eyeball looking down? And these are like the eyelashes of the eyeball. So I'll just draw it really quick. So this is my eyeball. I know it's a weird eyeball, but let's just pretend this is my eyeball. Here's my eyelashes. Whatever side my eyeball is looking at, namely 3√3, that's the opposite side. Okay, that's my opposite side. This is the adjacent side because it's actually touching the angle. It's actually making the angle. So this is going to be 3√3. And then this is going to be 3, which equals 2 1/2. You should simplify. And this is √3/2 because these would simplify, right? And last but not least, opposite, which would be 3√3/3. So it should feel funny because you're like opposite, adjacent. What are you talking about, Miss Johnson? And then I'll cancel these 3's. And so my answer here is √3. So if you're uncomfortable with this whole opposite and adjacent, you kind of should be, because this is the first time we've ever had to reference angles like this. And I kind of want to make sure that you're feeling okay about this. So now that you know how to do this one, go ahead and do this one and see if you could do it all by yourself and get the correct answers. And then come back to me so we can check our answers. All right, now that you're back, they want us to go from angle D, so that's the same angle. You can imagine that's my eyeball, and it's looking at the opposite side. So it's opposite over hypotenuse. In this case is 12, so I'm going to put 12 on the bottom for both of those. And then the adjacent side is next to the angle. Now, some of you are thinking, Miss Johnson, this was the adjacent this time, but over here, in your earlier example, this was the adjacent. So the adjacent's really just in reference to where the angle is. Is it next to it, kind of thing. So remember, adjacent means next to. So in this case, our adjacent side is 6, right? And I just said our adjacent side is 6, so I'm going to put that 6 on the bottom. And our opposite side is 6√3. So now I want to simplify my answers just so I can, simplify. So this would simplify with this, leaving a 2 on the bottom. So that's √3/2. 6/12 is equal to 1/2. And these simplify into 1. Now you should, 1√3. You should notice something. You should be like, hey, Miss Johnson, these answers are the same. And I'm like, yeah, that's weird, right? Because this triangle is way bigger. It's weird, right? So it's because we're talking about ratios and not side lengths, right? We're saying this big triangle's adjacent side to this big triangle's hypotenuse side. And the ratio means, like, because it's a bigger triangle, it will have a bigger hypotenuse and it will have a bigger adjacent side to angle D, but the ratio between them will still be the same. Does that make sense? Okay. So that's what we noticed from problem 3. It says, what can you infer about the angle measures of triangle ABC and DEF? And you're like, I don't know. What should I infer? And so we go back over here. Maybe the answer will be up here. And you're like, maybe I should simplify these, right? And so let me simplify these because maybe that'll help us understand. So let's do 5.5 divided by 6.7. That's just a weird number, right? So I don't know. This is about 0.82. And then what's 3.3? Oops. What's 3.3 divide... Point... Point... It's not letting me do point. There it goes. Divided by 6.6. And you're like, hey, Miss Johnson, that's half. Yeah, and that was what the other one was too, right? Let's do the last one, 5.7. Oops, keep doing that. 5.7 divided by 3.3. Oh, that's 1.7. And you're like, okay, Ms. Johnson, the only one that seems to match is that other one, right? And so what I want to do is I want to compare our answers to see if we compare those, right? So root 3 over 2, let's try root 3 over 2. Oh, that's pretty similar to that 0.86 though, right? And the other one is root 3. Oh, just root 3. So let's look at that. And that's at 1.73. So these are all the same. So it says, what can you infer? Where's that question? It says, what can you infer about the angle measures? Well, it must be the same, right, as this guy. It must be a 60. It must have a 60-degree angle in there. So it must be that this angle here is 60 degrees. And this one's 90. If this is 60 and this is 90, what's the small angle? And you're right, it's 30. So it says, why do the relationships you have noticed occur? And that's because of this factor, right? If I scale this drawing up, the ratios will still be the same as if I make them tiny, 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 right? The ratios between the sides, because you're the ones who told me that if my triangles are similar, then my sides are proportional. So that should be true. They will grow in proportion. So it says, measure the angles in both triangle ABC and triangle DEF. What can you conclude about the ratio? So if I had a compass that was digital, and I think I do have a compass, I don't know how to use it though. We would know that it was a 30, 60, 90 triangle, 30, 60, 90 triangle. And what might you conclude about the ratio of the sides that has a 45-degree angle? If necessary, draw an experiment. So what they want you to do is they want you to also learn about our other special right triangle, which is a 45, 45, 90. Okay. And then I will tell you right now, the way Miss Johnson draws it, if this is a 45, 45, 90, and you're going to see me draw this over and over again, you'll see that this is 1, 1, root 2 every single time. Now, sometimes Miss Johnson draws these as 1x, and x root 2, because remember, I can grow this as big or as little as I want, right? So the ratios we worked with in this task have special name: sine, cosine, and tangent. So if you've ever heard of this phrase, you'll hear me saying it a lot. So, oops, I can't spell. Toa. So means opposite over hypotenuse. Cosine means adjacent over hypotenuse. And tangent means opposite over adjacent. So you'll hear me saying these over and over and over again. Okay. So down here, it says your takeaways. The ratio called opposite over hypotenuse is called what? OH. And you're like, OH. Who is OH? Which one of these three is OH? And you're like, oh, it's so, which means sine. So when we write sine, sometimes you'll see me write it as that, S-I-N for shorthand. But when you're actually writing out the word, it's sine. Adjacent is ka. So I'll write this again. So ka toa. So this is cosine. And this is tangent. So this should be somewhere. So before calculators, these values were recorded in tables for reference. For each of the tables for include these values. So go ahead and fill all of this out. Besides SOHCAHTOA, I will have you write this somewhere. Put this in the front of your brain. I will tell you right now, the students who understand your 30, 60, 90 and your 45, 45, 90, and it's in the front of your brain, it's the equivalent of when students understood their multiplication tables back in 5th grade. Because imagine how difficult it was to do 5th grade math, 6th grade math, 7th grade math without knowing your multiplication tables. So these things right here, these two reference things, I'm going to reference over and over again. So this is going to be x, 2x, x root 3. And this is going to be x root 2. So if you can, take a picture, a snapshot of this, and put this on the background of your computer. Take it as a picture and put it on the background of your desktop. Make it somewhere. Put it on the top of every single homework. If we were in face-to-face, I'd make you draw this out for every single homework. Okay, on the top of your page, including on the top of your test. So these are so important that I will link another video that I just did for my integrated 3 students. Again, the more you understand this, the easier integrated 3 is going to be, especially in the chapters that they're going over right now. All right, have a great day. Bye.